This is kind of a crude photograph and a simplified explanation of atmospheric pressure, but hopefully it can be used to convey a deeper concept that we will address more in depth a little bit later. Refer to page 159 in your text for this explanation. The first set of cities represents equal elevations, equal temperatures, and equal surface air pressures. If that is the case, we can assume that there's the same number of molecules in each column above both cities. Because we have an equal number of molecules in each column above both cities, we have equal pressure. The same station pressure will be read at the surface in each of these two cities in this example. Take this illustration to the second set of cities. All remains the same, but the temperature over City 2 increases. We already learned that as air warms, molecules speed up, and as a result they must expand. Therefore, the column of air over City 2 rises in order to contain the same number of molecules to keep the station pressure the same. Now I'd like to point out something pretty interesting. Notice this. Remember, this is a crude illustration to illustrate a deeper concept. There are, in this case, 16 different rows of molecules in each column of air. There's the same number of rows in each, but there's a higher elevation on the warm side because warm air expands. So count up 5 lines, for example, on each of the different cities. And notice this. The 5th line over the cold city is at a lower elevation, lower altitude than the 5th line on the warm city. This illustrates to us that a constant pressure is at a higher altitude and warmer temperature. Now check this out. We'll move to illustration C. Suppose we remove the invisible barriers between the two cities. The air aloft would move from column 2 towards column 1 and start to sink. This would increase the pressure at the surface over City 1 and decrease the pressure at the surface over City 2. Fluid, which is air in this case, always moves from higher pressure to lower pressure. The pressure difference due to the temperature establish what we call a pressure gradient force. This causes the air to move from the higher pressure to the lower pressure. In this case, the air at the surface of City 1 moves towards City 2 and then rises. The difference in temperature created a horizontal difference in pressure and consequently horizontal movement of air. This illustration of air moving in a circular motion from high to low is illustrated in your text in figure 6.3. Here's one more illustration of how a line of constant pressure varies in altitude with temperature. This illustration with a description can be found on page 165 of your text. This is a cross-section of a constant pressure map at 500 millibars, and you see there that there's an average height of the 500 millibar level, yet it's more of a contoured line in reality. This is due to the differences in temperature. The warm temperature, the 500 millibar level, is going to be at a higher altitude above sea level, while the colder temperatures will yield a lower altitude above sea level at that same pressure level. This is because warmer temperature yields a higher altitude above sea level, greater expansion of the molecules, while cooler temperature, more condensed air molecules, yields a lower altitude above sea level for the constant pressure.